Did you know that cells in our bodies can experience stress in many different situations? For example, they may be stressed when the supply of oxygen or nutrients is limited. They will be also quite stressed in certain mechanical loading situations. For example, cells are unhappy when the mechanical stress on their surrounding fibers is too high, or when these fibers are damaged, for instance, due to mechanical overloading. Cells in the tissue are programmed to react to these unfavorable conditions. For example, they will attempt to restore the tissue when it is damaged, and this way they hope to go back to the normal mechanical state of the tissue or tissue homeostasis. However, the reaction of the cells might not be sufficient in every case, and it might be impossible to restore this homeostasis. In that case, the cells end up burning out, and the tissue gets into a maladaptive state where it's impossible to restore the normal healthy conditions. Specifically in arterial tissue, cells are in their happy state when they experience the resulting wall stress and wall shear stress due to a typical pulsating blood pressure. Any deviating load will trigger a cellular reaction, and this is not unimportant given the numerous patients suffering from cardiovascular diseases. These cardiovascular diseases even constitute the leading cause of death globally, according to the World Health Organization. Let's, for example, think of an aneurysm, which can be a life-threatening disease in some cases. An aneurysm is a local dilatation of an artery, and if we look at the simple Laplace's law for pressurized tubes, then we can see that the circumferential stress in the wall will increase along with the increasing radius of the aneurysm. And so what the cells will try to do, they will try to produce more material in order to increase the thickness of this wall, such that the stress can reduce again. But often they fail to do so, which leads to an unstable situation where the artery keeps on growing over time. Surgeons can replace the diseased part of the tissue by a synthetic graft, while they shortly cut off the blood flow by using a clamp. But also this clamping is a form of mechanical overload that has proven to damage the tissue. However, on the longer term, the tissue heals and the functional integrity is restored. Another type of surgery that causes overloading in the tissue is balloon dilatation, which is used when there is plaque buildup that hampers good blood flow. The healthy part of the tissue gets overstretched, causing a maladaptive tissue response, leading to restenosis and the reclosing of the vessel. So we saw two examples of surgical overloading to arterial tissue, where we either get healing of the tissue over time or further degeneration. Now, the goal of my PhD was to understand these processes further through computational modeling. Because if we can understand these processes, we can also try to optimize certain surgery to steer them in the direction of healing rather than degeneration. But before we can develop these computational models of adaptive processes, healing or degeneration over time, we first need to know what the properties are of healthy arterial tissue. The mechanical properties of the tissue can be derived from planar biaxial tensile tests, from which we obtain stress-strain data points in two directions. These can then be used to fit the parameters of an hyperelastic material model. There are two reasons why this is not as straightforward as you might think. The first reason is that we will choose a reference configuration or zero strain state as the in vivo configuration of the artery, which is not the same as the zero stress state. The reference configuration is known from medical imaging, whereas the zero stress state, to know that one, we would have to excise the artery out of the body. Another reason is that there are multiple constituents in the tissue, and they can all have different zero stress states. And this is because material that is turning over at a lower rate will be stretched more in the wall than material that is constantly turning over. And so to account for all these reference shifts, I made a new method to do parameter fitting for arterial tissue. Once we have an appropriate material model, we can implement it into finite element software for our mechanical analysis. It took my colleagues and I quite some time to figure out how to do this properly for anisotropic fiber-reinforced hyperelastic materials. And since this is a common problem in the soft tissue mechanics community, we published an extensive tutorial. The final step to create the model is then to implement the time-dependent properties of the tissue. For that, I took into account a number of cellular processes that are turned into sets of ordinary differential equations. And so with this model, I was able to reproduce clinical observations or results that we obtained from animal experiments at the Department of Cardiac Surgery, and this in different applications. And this brings me to the first benefit of using computational studies in this context. The European Commission mandates to follow the policy of the 3 R's when it comes to animal trials. First of all, reduce the number of animals where possible, then refine the study in order to increase the well-being of the animal, and finally replace the animal trial by something else, such as a computational study. Such a study can be very complementary, and moreover, its economic and especially ethical burden is a lot lower. Computational models can also be used as pre-surgical tools for the patient-specific optimization of a certain surgery. For example, the characteristics of a certain patient can be used as input parameters to the model that predicts the long-term outcomes of balloon dilatation. We can, for example, input the patient's age and blood pressure, but also the specific plaque geometry, and then virtually test different balloon shapes, inflation pressures, etc. to find the best possible long-term outcome. Professor Inge Fourneau, vascular surgeon, is already convinced.
I'm very intrigued by the idea that the study of biological processes that are very complex are tried to be simplified by mathematics. And just the idea of someone trying to do so is bizarre. In the meantime, I have changed my ideas, and I think that this mathematical approach is an essential part of the study of those biological processes, as it helps to structure the very complex problems.